I'm going to do one last example from section 7.5. In this case, we're integrating a rational function, but the degree on the top is the same as the degree on the bottom, so it's not a proper fraction, or it's not a proper rational function. Like usual, we want to try to rewrite this, but by factoring the denominator as x minus 2 times x minus 1, you might think, well, can you split it up as a number over x minus 2 plus a number over x minus 1? That won't work, because if you cleared the fractions here, you'd have a quadratic on the left, only linear expressions on the right, and that would lead you to a system with 3 equations and only 2 unknowns, a and b. Okay, so that does not work. Okay, you got to try something different. Okay, and what you need to do different is turn this into a proper fraction. Okay, the way to do that is to use polynomial long division to rewrite this as a polynomial plus a proper rational fraction. Much like when you take an integer and divide it by a smaller one, you write that as a whole number plus a fraction. Alright, so we're going to do polynomial long division. The divisor is x squared minus 3x plus 2. What we want to do is ask what number do we multiply, or what quantity do we multiply x squared by. To imagine x squared below, okay, we see that we get, in that case, okay, so we want to ask ourselves, what do we multiply on top by? What do we multiply x squared by? Look at the leading term to make it match up with the x squared, in this case from our dividend polynomial, and that's the number 1. We got to multiply x squared by 1 to get x squared, and then multiply each term by 1, we get x squared minus 3x plus 2, and we're going to subtract that from the dividend to give us our remainder, 3x minus 2. Now in this case, the remainder has smaller degree than the divisor, so we're done. We can't divide it anymore. Okay, I'd like to just compare that situation to a numerical example. So suppose you take 3 and divide it into 17. We know it goes in there 5 times with a remainder of 2. Okay. Now, what we just did there was we took 17, we subtracted off 3 times 5, and what we're left with is 2. Another way to write that would be that 17 is equal to 3 times 5 plus 2. Or, dividing each term here by 3, we get that the fraction 17 thirds is equal to 5, a whole number, plus 2 thirds. So we've got the dividend over divisor is equal to the quotient plus the remainder over the divisor. Same thing happens over here. The dividend over the divisor is going to equal the quotient, which in this case is the number 1, plus the remainder, which was 3x minus 2, over the divisor. Excuse me. Alright, so now what we want to do is split this up by partial fractions. We're going to be able to integrate the constant function 1 no problem. We're going to split this up, so factor the denominator as x minus 2 times x minus 1. And now this will work, this decomposition. Okay, a number over x minus 2 plus a number over x minus 1. We're going to see when we clear the fractions out, multiply everything by the LCD, we're going to get a linear expression on each side. Okay, so we get 3x minus 2 is equal to a times what doesn't cancel, which is x minus 1, plus b, which didn't cancel. We multiplied the last term by x minus 1 times x minus 2. Now rewriting these, we get a plus b times x plus the constant term is negative a minus 2b. So that leads us to compare coefficients. Okay, the only way these two linear polynomials are going to be the same is if they're actually the same. They have to be the same for every value of x you plug in. Now, the easiest way to solve this is to just add them together, because the a's cancel out when we do that. We get 1 is equal to negative b, which tells us b is equal to negative 1. Plug that into, say, the first equation, and it gives you that 3 is equal to a plus negative 1. And then solving for a, we get that a is equal to 4. Okay, so now we're going to go back in and plug in a is 4, b is negative 1 in here. Okay, and that's going to help us to evaluate this integral. Alright, So first thing, we're going to say that that integral is equal to, just by polynomial long division, the integral of 1 plus 3x minus 2 over x minus 2 times x minus 1, which is our divisor over here in a factored form. Now we can integrate this no problem. This we just figured out the partial fraction breakdown for. So we get the integral of 1 dx plus the integral of a we got to be 4, so it's 4 over x minus 2. B was negative 1, so that's minus 1 over x minus 1. Each of these are natural log type integrals. Pull the constant 4 out, for instance, and you get natural log of x minus 2, and then minus the natural log of x minus 1. Again, you can do a u substitution if you need help to see that. Now, your textbook might write that instead of writing 4 times natural log of x minus 2, they might write absolute values inside, or you might, and same thing for the last term, you might see natural log of x minus 1, or the absolute value of x minus 1 inside. Okay, either one of these are acceptable. This is a more general answer. Okay, the domain of this function is larger than the domain of this function.